Okay, today we are going to be talking about chemical reactions and how you can determine whether or not a chemical reaction has occurred. First chemical reaction, burning. Second, noise. Light. Here we have a demonstration of several different things that demonstrate whether or not we have a chemical reaction. Here's the big boy here. Check this out. Okay, so we start by lighting the match, light the fuse, and whoa! Did you see that? Wow, that's a big boy. Alright, the next chemical reactions I have for you, we'll take you indoors. Next chemical reactions are a change of color. If we have a change of color, a chemical reaction has occurred. So here you see a blue substance and a white substance, or clear actually. If we take this clear substance and pour it into the blue substance, you would think it would just be maybe diluted blue. However, let's see what happens. Oh yeah, there we go. Very nice. Very nice. Alright, our next chemical reaction. So we have a change in color. We have light. We have heat. We have sound. And one of the last ones is, here we have a solid, and we're going to mix it with a liquid. And oh my goodness, what happens there? A gas is given off. Nice. So a gas is given off. That is also a sign of a chemical reaction. Our last chemical reaction, which I cannot make with household products that I know of, we have it back at school, would be to show a precipitate. And that would be if you put two liquids together and then a solid would precipitate out of it. So we would get a solid out of combining two liquids together. And usually that would be an aqueous solution, meaning it would be within a liquid. Okay, so today we're going to be learning about balancing equations also. Bear with me a moment. Actually describing what we'll be also learning today is about chemical reactions. A chemical reaction is a process by which one or more substances are changed into one or more different substances. Any chemical reaction has reactants, and if we're writing with an equation, here is a chemical equation. The reactants would be on the left-hand side of the equation, and the products on the right-hand side of the equation. These cause these, or we could say this arrow means yields these two products. According to the law of conservation of mass, the total mass of these reactants must equal the total mass of the products. So the mass is conserved. Even if, when you saw the reaction of the gas being given off, if we massed the product that was left, it would be lower. But if we could capture that gas that was given off, we would also be able to see that the amount of mass given off in the gas plus what was left in the glass would equal the original reactants. So this we said is a chemical equation, and we use these symbols to indicate the formula. We've learned that these symbols indicate the particular elements, and the subscripts indicate the number of atoms. If we have coefficients in front, that tells us how many molecules or how many formula units we have. So here's our example of nitrogen, chromium 3 oxide, and water. Nitrogen gas, chromium 3 oxide, and water is our product. Our reactant was ammonium dichromate, and it would break down to these two products. Okay, you also see some little symbols in parentheses. The S stands for a solid, meaning it started out as a solid, and as it broke down, nitrogen gas was given off, and also water as a gas was given off. That would be in the form of water vapor. And here you notice that the chromium 3 oxide is a solid. And another way of showing a solid would be arrow down, and this typically indicates that it's precipitated. If we don't use a G, we could use an arrow up for being gas given off. All right, we could have word equations. We could see our equation as methane plus oxygen will yield carbon dioxide plus water. Okay, that would be a word equation. Methane plus oxygen yields carbon dioxide and water. Okay, we can convert that word equation to a chemical equation. Here we have methane gas plus oxygen gas yielding carbon dioxide as a gas and water also as a gas. All right, but notice something about this equation. Remember we said that mass had to be conserved, and we needed to make sure that our equation was balanced. Just like putting things on a balance, the one side has to equal the other in order to balance out. When we're doing mathematical equations, the equal sign is a balance, meaning the left-hand side always has to maintain an equal balance with the right-hand side. Well, same thing with chemical equations. So as we look at this equation, we notice that we have one carbon on this side, one carbon on this side. Oh, carbon balances. We notice that we have 4 hydrogens on this side, but if we look on this side, we only have 2. Here we have 2 oxygens, but on this side we have 1, 2, 3 oxygens. So our equation is not balanced. I'll show you a balanced equation, and then I want you to go to the other link that we have for you at Mr. Higley's website, which will take you to bosemanscience.com, and he is kind of like a new Khan Academy, and he will show you how to balance equations. But here I've balanced this methane equation for you. And you notice by adding coefficients, we can balance our equations. So now, if you look, we have one carbon, 4 hydrogens, and by putting a 2 out in front, we have 2 times 2, we have 4 hydrogens. But now this makes 2 oxygens. 2 plus 2 is 4 oxygens. Well, by adding a coefficient of 2 out in front of this oxygen, 2 times 2, is 4 oxygens. So now this equation is considered to be balanced. Thank you for joining us today, and I hope you enjoyed this message.